All right, so here is the Unit 3 free response question was worked through. All right, so the first question answered the following questions related to xenon. And so you have, it shows the particulate level view of liquid xenon. And it wants you to, in this one, draw the solid, and this one, the gaseous form. And if you notice, the solid one, which is on the left, is compact. It has less space between the molecules, and that's because they're strong intermolecular forces. If you look at this side, that is the gaseous version. They're less compact, more space between the molecules. There are weaker IMFs, so that's why it's spaced out like that. Okay? So that takes care of that one and that one. All right? Now, this next one, it says, let P and V represent the pressure and volume of xenon in the container, that one right there. If a piston is used to reduce the volume of the gas to V/2 at a constant temperature, what is the new pressure in the container in terms of original pressure? You need to remember Boyle's law. The initial pressure and the initial volume are equal to the final pressure and the final volume at a constant temperature. So that's basically asking you to apply Boyle's law. So if we have initial pressure is P, initial volume is V, the final pressure we're trying to find, and the final volume was V divided by 2, using Boyle's law, rearrange it, and you end up with the final pressure is 2 times the original pressure. Pressure is double, okay? And that's just an algebraic rearrangement of that equation, okay? So, then it says, describe what happens to the average speed of the xenon atoms in the container in diagram 3 as the volume is reduced to V/2, so at a constant temperature. Well, the average speed will stay the same because the temperature is constant. When you keep the temperature constant, the speed stays a constant. This is going back to our discussion about kinetic molecular theory. So that takes care of that. Now, number 2. Answer the following questions about solutions of sodium chloride and calcium chloride. So I'm going to go ahead and show you the whole thing and walk you through it. All right? So we had this over here. If you look at it, you have 1, 2, 3, 4, 5, 6, 7, 8 chlorine, and you have 8 sodium. So you have 8 moles of chlorine, and you have 8 moles of sodium. They fully disassociate. And so when you fully disassociate them, that tells you a lot about it. You can actually calculate the volume of this, and you'll need that to do the next step. So to calculate the volume of sodium chloride, we take the moles of sodium chloride, which we have 8, and divide it by the molarity of this solution, which was 8 moles of sodium chloride, and it was 0.2 molar sodium chloride, and that gives you a value of 40 liters. Use that information to plug in here. You're trying to calculate the volume. Well, you know the volume is going to be the same. It's the same thing. It doesn't say anything different, so you can assume that. We're actually trying to find out the moles of calcium chloride. So we plug in the values that we do know, 40 liters, 0.1 molar, and we're able to figure out that we have 4 moles of calcium chloride. Using that information, we know that the balanced reaction is this. CaCl2 is a reversible reaction producing, when it dissociates, calcium plus 2 ions and 2 moles of chlorine negative ions. We started off with 4 molar, 0, 0. We ended up with 0 molar and 4 and 2 moles times 4. So we end up with 4 calcium and 8 chlorine. So that's where we get that number. Okay, there's 8 chlorine and 4 calcium. So you just see how it goes. You use that information to get to there. All right. And then this one right here, briefly explain the presence of charged ions in the ionic solids, such as sodium chloride, how it explains why sodium is soluble in water, or sodium chloride is soluble in water. The anions and cations are attracted to the polar water molecules, just like this. You have a partially positive side, a partially negative. So the positive is attracted to the partially negative, and the negative is attracted to the partially positive. And then this is just a simple stoichiometry problem. And so you're looking for 850 to 870, but I got 860 milliliters. So I hope that helps you out, and I will see you